Okay, so ready?
Yes.
Okay, shall we? Can we start? Yes? Okay. Very good. So, are we recording now? Yeah, okay. So, hi everybody. Hi everybody. So, today we are going to continue the model categories topic with the definitions of derived functors and Quillen adjunctions. So, once preparing this talk, I realized that I need to make a disclaimer. So, we will provide plenty of information during this talk, some propositions, some theorems, but we are not going to prove much of them. And this is because, well, first, it is a reading seminar and it is not on model categories. There is plenty of technical stuff hidden behind. So we'll just go over this to get basic ideas what model categories are. Okay, so let me start from recalling what we did last time, or actually what we finished with last time. So last time we finished with the notions of left and right homotopy. Okay, so I will quickly recall the definitions only for the, say, left homotopy. The right homotopy will be dual. So the definition was as follows, that a cylinder object for A is an object A smash I. So here I should make also a remark. Here we treat A smash I only as a notation. It is in particular in what's the word? Any model category, cylinder object doesn't have to be a product of anything with anything. Okay, so here we treat A smash I just as a notation. So we need, what we require from a cylinder object is that it comes with a map P and weak equivalence to A, such that this composite factors identity on A plus identity on A. Okay, so this is the definition of a cylinder object. Last time at the end, there was also a question why a cylinder object exists for every object. In the model category, actually, this is very simple. So if we have a map from A, disjoint union A to A, so the folding map, then by the axioms of model category, we can factor this map as a cofibration followed by a cyclic fibration, right? So this is how we obtain a cylinder object for any object A, and moreover, this obtained cylinder object is what is called good cylinder object, because the map from disjoint union to the cylinder object is a cofibration. Okay, having a cylinder object, how we define a homotopy. So if we have two maps, then we say that F is left homotopic to G if there exists a cylinder object A smash I such that, sorry, there was a question? No, okay. You sneezed. Oh, it's okay, Asha. Such that we have this composite. Yes. So okay, what we have here, no, over here. Okay, so what we need for a left homotopy to exist is this map. So we need a map from a cylinder object to X, such that if we take the map P coming from the definition of the cylinder object, followed by H, then this composite is the same thing as F plus G. So here I mean a product of these two maps. And I just wanted to quickly say and kind of recall from last talk that really what we are doing is repeating ideas from topological spaces. Because in topological spaces, if I have some space X, and I have this joint union of X and X, then I can take its cylinder object to be, well, just cylinder of X. And what is a homotopy between maps from X to some other space Y? Well, so a homotopy is a map from the cylinder object, so X cross unit interval in this case, such that if I go by via the 0 inclusion, I will obtain map F, and by the 1 inclusion, I will get map G. So what is this definition doing? It is kind of generalizing and making abstract notions out of this idea. Okay, so now what we are going to do is we are going to juggle a little bit with definitions inside the model category. So one of the things which we would like from a homotopy relation is that it would be nice to have it as an equivalence relation, but it is not always the case. And when it is the case, so if A is cofibrant, which means that the map from initial object to A is a cofibration, then we have two properties. So left homotopy relation, this is the notation for the left homotopy relation, is an equivalence relation on morphisms in our category, our model category C from A to some other object X, and the left homotopy implies the right homotopy. So here I was trying to find an example such that it justifies the cofibrancy assumption here, but I wasn't able to. And yeah, I asked it on Math Overflow and I still have no example. Yeah, I know, Math Overflow is an ongoing thing. So yes, and if we have such a statement, then we will have, of course, the dual statement that if X is fibrant, in other words, the map from X to the terminal object of the category is a fibration. I didn't, we did it last time. Yeah, so I just recalled the definition of a left homotopy, and definition of right homotopy is just dual. But if you want, I can repeat it. So, okay, if X is fibrant, then the right homotopy relation is an equivalence relation on homomorphisms, on morphisms in our category from A to X, and right homotopy implies the left homotopy. Okay, so one thing which we can see is that in order to define a homotopy relation just between maps, we need to have maps from a cofibrant object to a fibrant object. Then the notions of left and right homotopy will be the same, and homotopy relation will give us an equivalence relation. So now we will use this kind of observation to define the homotopy category. And to do this, firstly, we need to say what is a cofibrant replacement. So for each object X in our category C, we can factor the map so a map from the initial object to X as a cofibration to some object Qx followed by a acyclic fibration. So this is one of the axioms of the model category why we can do this. And what we get is a cofibrant object Qx, which is weakly equivalent to X. And this Qx is called a cofibrant replacement for X. I don't know yet, but having a functorial cofibrant replacement is a stronger assumption, right? Yeah. So no, right now we are taking general cofibrant replacement. The only assumptions which we are taking is that if X is already cofibrant, then its cofibrant replacement is equal to X. And so this is the cofibrant replacement, and similarly, we obtain a fibrant replacement and we'll denote it by R of X. So right now we defined only cofibrant replacement for objects, but also cofibrant replacement will give us a sort of a functor to some other category. And to do this, we need to see what cofibrant replacement is doing on maps. So there is a lemma saying that given map f from X to Y in C, there exists a map f twiddle from the cofibrant replacement of X to cofibrant replacement of Y, such that, so the following diagram commutes. We have Qx, here we have the acyclic fibration to X, here we have F, here we have Y, Qy, and here we have F twiddle. So this diagram commutes. This is one of the assumptions. Sorry, this is the statement dot, and moreover, so F twiddle depends only on the, well, we can choose either left or right homotopy class of sorry, it depends only up to homotopy. This is what I should say firstly, only up to homotopy. Left, right homotopy only on F. So what this statement is saying that a priori I can have plenty of such F twiddles, but they will all be left or right homotopic, depends on my choice of the relation. And if Y is fibrant, okay, I'm not sure if I will have enough place here, so I will do a maneuver. So this sentence will be continued over here. And if Y is fibrant, then F twiddle depends only on the left homotopy class of F. Of course, depends up to left or right homotopy. So yes, what this addition is telling me is that if Y is fibrant, then all of the choices of F twiddle are homotopic and depends only on the left homotopy class of F. Okay, so a priori, if Y is not fibrant, and I have two left homotopic maps F and G over here, then their lifts might not be homotopic. But if Y is fibrant, this is not anymore the case. Yeah. Thank you very much. And one more thing, F twiddle also is a weak equivalence if and only if F is. Okay.
This Y is fibrant or always?
No, this is sorry, this is always. So I messed a little bit with order of statements. So we can actually prove this stuff. So I will only prove here the existence of F twiddle. Yes, in order to show the ideas of how we are proving stuff in model categories. So because Q of X is cofibrant, we have this map and it is a cofibration. Then we have Qy, this is also a cofibration, but it is not important for us. And here we have Y, this is a fibration, but also a weak equivalence. So this one over here is a acyclic fibration. And I can here have the map, so I can go to X and then I can go to F. And this is how I define this map over here. So this is F followed by P. Okay, so what I have is I have a diagram where this arrow is a cofibration, this arrow is a acyclic fibration. So what I can do, I can lift this map to F twiddle. And this is how we define F twiddle. Okay. Right. So using this, okay, are there any questions so far? Okay. So let's gear up the abstraction a little bit. So using Qx, we can define a functor Q. So maybe not using Qx, but using cofibrant replacement. From our category C to the category P of CC. So this is our starting model category, and this one over here is a category of cofibrant objects of C and right homotopy classes of maps as morphisms. So, well, in order to say that there is such a functor, I needed this lemma which I just provided. So this functor is sending each object to its cofibrant replacement, and a map by this lemma, it is sent to f tilde, sorry, f twiddle, or rather right homotopy class of f twiddle. So it is well-defined functor, and moreover, the restriction to another subcategory induces a functor q prime going from phi c f to I might have a mistake here. Yes, pi c c f, I think. So I need also to tell you what are these categories. I will just take some color. So this one over here is the category of fibrant objects and left homotopy classes of maps. And over here we have fibrant, cofibrant objects, or rather I should say cofibrant, fibrant objects. And here I can say just homotopy classes of maps. Because if I have a map between cofibrant, fibrant objects, then the notions of left and right homotopy coincide. No, so this is correct. So when, yes, I was also wondering about it, and as usual, I don't have good answer for this. But no, we are supposed to take a category of cofibrant objects and right homotopy classes. Maybe the reason is that if you take left homotopy class of maps, then there will be right homotopy classes of maps, right? But a priori you might have more. You know, you might have might have morphisms which are right homotopic but are not left homotopic. And ditto for pi CF.
But then do we know that it's equivalent?
Which one?
Right homotopy.
What about? No, it is not.
So you're just taking the equivalence class.
Yes, I'm taking, yes, you're right. I should have said this. So here by homotopy classes of right homotopy classes of maps, I'm saying that the equivalence relation generated by the right homotopy. Okay, and for this, for saying that we have such a functor from the fibrant objects and left homotopy classes of maps to cofibrant fibrant objects, I needed once again this lemma. So I'm taking a fibrant object, I'm sending it to its cofibrant replacement, so I'm getting something cofibrant fibrant, and because of this lemma, this f twiddle depends only on the left homotopy class of the map which I'm sending from.
You mean by CC, right?
Where about?
Because you say it's
Here?
fiber and it's not down, like you where CC
Yes.
is a category of cofibrant object and right homotopy classes, so
Yes, sorry, you're right. Okay, so this should be pi of CC. Okay, so we have the same constructions for R prime. Sorry, dually for the fibrant replacement. So we can play the same game with fibrant replacement. And now we are in a position to define the homotopy category. Is the category where with the same objects as C, and so morphisms in the homotopy How about now? Okay. Oh, somebody said that there is a problem? Or?
No, I've been monitoring it, so I thought
Okay.
it might happen.
Annoying. Okay, very good. Okay, so one of the things with model category theory is that, at least for me, once you make this definition, you don't really see what are homotopy classes of maps. We'll provide a more conceptual definition in a moment, but yes, so I will come to the bigger idea just in a moment. So one of the things which comes with the definition of a homotopy category is that there is a functor gamma going from category to its homotopy category. So gamma on x is equal to x, and gamma on some map f is r prime q of f, going from r prime qx to r prime qy. Sorry?
How is it from? How to see it from? Oh, okay.
Yeah, okay. A couple of remarks on this functor. So
you don't have to call it R prime though, right? R also makes sense.
second.
You don't have to call it R prime, right? So R is, you could have just called it R.
Yes, but I defined these maps as
Because R prime is defined as R.
not really with different R prime. So it is the same. So Q is defined as a functor from C to pi of CC, right? So R will be defined as a functor from C to pi CF,
Yeah, but
and then R prime is defined from pi CC to pi CCF.
but it is just a replacement.
Yeah, I mean, you can also probably write it as RQF. Well, okay, not really, because what are you doing is QF is taking you into the category of where your maps are.
Oh, you're taking a quotient before.
Yes,
Not literally the same thing.
yes, exactly. Yeah, so if you wanted to write R, there is some choice of representative in the middle happening. Okay, so a couple of remarks about this functor. So if both X and Y are cofibrant fibrant objects, then gamma from morphisms in C from X to Y to morphisms in the homotopy category from X to Y is surjective. And induces a bijection so by once again, I didn't define this. Pi xy means just homotopy classes of maps, because both objects are fibrant cofibrant. Then it doesn't really matter whether I take left or right homotopy. Here I have homotopy classes of maps from X to Y. So really, the upshot of this whole discussion is that the homotopy relation, as we understand it in well, as an intuition coming from topological spaces, is defined properly only for fibrant cofibrant objects. Okay, and moreover, gamma of F is an isomorphism in the homotopy category if and only if F is a weak equivalence. Okay. And this statement over here will kind of serve us as a starting point to the next definition, other definition of a homotopy category, more, let's say, conceptual one. And to do this, we'll need a notion of a localization of a category.
We could have done this construction in one step, right?
Which one?
Take the cofibrant fibrant replacement. First take the cofibrant replacement, and then take the fibrant replacement. That's your object and the target, and then just take. We have to do it in 2 steps.
I don't know, but then how you define maps between fibrant replacements?
So pi CCF is already defined, right?
Yes.
So this is your target.
Okay.
And you start from C.
Okay.
Take an object, take a cofibrant replacement, and then a fibrant replacement. This is the map. And then you do F tilde, and then whatever corresponding thing is for R, and then this is your morphism. Maybe it's easier to prove things in that way, but you could have just.
Okay, but I don't really. So why is it done in 2 steps? Is that Q as a functor is it doesn't take you anywhere here, right? So you need to have as a target of this functor category of cofibrant objects. So that's fine, but as a maps, you need to take right homotopy classes of maps, right? You cannot take just maps on the nose, because then, well,
That I agree, but I'm saying just don't do the middle step. Just skip the middle step.
yes.
That works, right?
No, I mean, I don't.
I'm saying,
Okay, but okay, composite of the two you can do, but then the problem is, I think, with maps, because then you need to, well, how you would define fibrant cofibrant replacement. So we are firstly taking cofibrant replacement, and yes.
But you can just choose one, right? Replacement, and then replace it with another replacement, and then show that.
Okay, so we are more or less saying then, okay, instead of doing this, then all of the maps in the right homotopy class will be sent by the fibrant replacement or whatever to the same homotopy class or something like this, right? So instead of taking pi over here, we are saying that r prime of, or r of f. Okay, I'm not sure if I can repeat it. I see the idea, but then I think this is more or less the same thing.
Yeah.
Because in order to define fibrant cofibrant replacement, you would need to say in the middle that for every map in the right homotopy class, my functor is doing this. So instead, we are saying this. Okay, so coming back to localization idea. So a definition, let C be a category and W will be a class of morphisms in this category. Then we say that the functor f from C to D is a localization of C with respect to D, with respect to W, if, so firstly, f of f is an isom for each map in my distinguished class W. And secondly, I have a kind of universal condition. So whenever G, so G is another functor from C to D prime, is a functor such that G of f is an iso for all f in W, then there exists a unique functor G prime from C to, from D to D prime, such that D prime, so I have G over here, D, F, and here I have G prime, and this diagram commutes. So in other words, a localization of a category with respect to a class of morphism is a functor, firstly such that all of the classes in the, all of the maps in the class W are taken to isomorphisms via F, and this functor, this localization functor, is universal among functors with this property. Okay, so in other words, we can think about localization of a category with respect to some class of morphisms as artificially adding inverses of the morphisms in W. Okay, and this will give us, using this statement over here, a more conceptual description of the homotopy category, because let C be a model category. Then gamma from C to the homotopy category of C is a localization of C with respect to the class of weak equivalences. So here there are two things, two kind of remarks in place to do. Firstly, due to this theorem, we can see that the homotopy category depends, sorry? Yeah, depends only on the weak equivalences. So a priori, what we can do is, in order to discuss a homotopy category or homotopy relation, is just define weak equivalences. And there is a notion of, I think, homotopical category, something like this. So this is just a category equipped with weak equivalences. Yes, but the problem with the localization construction is that it is not very well behaved in general. So there are examples, for example, of locally small category and the class of morphisms in this category, such that the localization with respect to this class is not anymore locally small. In other words, we are having morphisms between two objects in our starting category, and this is a set. And once we localize this category, it will not be a set anymore. It will be too big. So the idea of model categories is providing us two things. Firstly, it is taming such kind of unwanted behavior. So in model, if we have model category, then localization will be of a locally small category will be always locally small. But also, maybe it is not yet clear from this definition, it gives us an idea how to construct and how to study homotopy category, right? Because if I only told you what are weak equivalences on topological spaces, it would be hard to work out what is the homotopy category of topological spaces. But then we know that in the topological spaces, all objects are fibrant. And what are cofibrant objects? These are retracts of CW complexes. So homotopy category of topological spaces with classical model structure will be just a category of CW complexes and homotopy classes of maps with it. So what I'm trying to say is that this statement and all of the idea of cofibrant, fibrant games is giving us more or less constructive approach to studying homotopy theory. Okay. So now, if we have two model categories, we would like to compare them somehow. And compare the homotopy theories which these model categories describe. So now we'll go to the next goal, which are derived functors. Okay, so Here we'll start with C be a model category. And D, sorry, we will have a functor from C to D. So this is just a functor. Now consider pairs G as consisting of a functor G from homotopy category of C to D and as a natural transformation S from what I want G gamma to F. Yes. So a left derived functor of F, if it exists, is a pair LF T. So a pair, of course, of this type such that, so it will have a universal property. So if, once again, we have GS is another pair of the type above, then there exists a unique natural transformation. Is this notation clear? Do you use it? Or okay. A unique natural transformation as prime yes, just a moment, I will just finish writing this. G to LF such that the composite G gamma going to S prime composed with gamma going to LF gamma going to T F. So this is the same thing as the natural transformation S. So this is supposed to commute. Gamma is a functor defined over here. So gamma is a functor standing from C, from a model category to its homotopy category. So gamma, G gamma is, I'm going firstly to the homotopy category and then I'm going to G. Yes.
Why is gamma a little bit down? It's just a composition of functors.
Yeah, I mean, this is a composition of functors. Do you want me to write like a circle in the middle?
Yeah, it seems like you.
Okay.
Yeah, you just gather a little bit down, right?
Yeah, this is
what okay, I see. Yes. Okay, so a priori, well, it would be too nice, and it wouldn't be probably interesting notion if left-derived functor existed for all functors. So in order for a left-derived functor to exist, a functor needs to satisfy some conditions.
What is this or right hand?
Which one?
Derived.
Yeah, but okay, but how do you see it as a Khan extension of what? So we are taking homotopy category.
Gamma and F.
Okay, I see. So you have C over here, you have gamma over here to homotopy category. Here we have what?
Yeah,
F to some other category D. Okay, so this is the left canal extension.
it's like homotopical limit functors. If F is the limit.
Okay. Yes, yes, I'm going to answer this question now. So the question sounds as follows. When LF exists, or probably to put it more grammatically, when it does exist. Okay, so the answer is given by the following proposition. So we have a setup as follows, as here. So we have a CM model category and the functor F from C to D. So we want it to be a functor such that firstly, f of f is an isomorphism if f is a weak equivalence. Okay, and is a weak equivalence between cofibrant objects in C. Sorry, there is no more conditions. There is only one condition. Is an isomorphism if F is a weak equivalence between cofibrant objects in C. Then LF exists, and for each cofibrant object X of C, the map Tx going from the left derived functor of X to F of X. So this is an isomorphism. Okay, so this answer gives us an answer when the left derived functor exists. And yes, once again, I'm not defining here the right derived functors, but this will be a dual notion, completely dual notion to the left derived functors. And then we'll have the statement, then the right derived functor exists if it is an isomorphism, if F is a weak equivalence between fibrant objects. Right?
But yeah, exactly like the colimit is if we have cofibrant objects and the colimit is like preserve equivalence, right? We have equivalence. The colimit become homotopy. So yeah, so it's left it's for the colimit, not the limit.
Yeah, so this is what we discussed here. So the left derived functor is a left can extension over here of this diagram. So we have here the functor gamma sending C to its homotopy category, and here the functor which we want to derive. Yes.
I mean from the FF is a colimit. If F itself is a colimit, then LF will be the homotopy colimit. And you can see there in this proposition that one of, if we want want, like we do cofibrant replacement, right? To do so this is say like if you have a cofibrant, if you have equivalence between cofibrant, then it's going to isomorphism.
Yes.
This is what happened in the colimit, like regular colimit. You will have cofibrant replacement.
Yeah, I had some comment here, but I forgot it. Okay, but let us continue. So actually what is of interest of us is that if we have C and D, if we have two model categories, we would like to compare homotopy theories coming from these model categories. Okay, so a definition here. Yes, so once again, we have a functor between two model categories now. Then, so I will write this between model categories. Then a total derived functor, left derived functor, LF of f is a functor so let's write it as this. So this is equal by definition to gamma d composed with yeah, just a moment. No, sorry. So this is a left derived functor of the composition gamma d composed with f, which goes from C to the homotopy category of D. So in order to obtain the total left derived functor of f, what we need to do is we need to take left derived functor in the sense of this definition up there of this functor. Okay, now the central idea, okay, maybe not central, I'm not kind of qualified to say this, but important idea are Quillen adjunctions and Quillen equivalences. So this is supposed to tell us when, even though the categories are different, their homotopy theories are the same. For example, well, we'll give this example, but if we want to study homotopy theory on topological spaces, we can as well do it with topological spaces or simplicial sets. And why is that? This is because these two categories are Quillen equivalent. So let us discuss this in the form of the theorem. So let C and D be model categories. And F, so here we'll have a pair of adjoint functors. Be a pair of adjoint functors. So suppose that F preserves cofibrations and G preserves fibrations. then the total derived functors so LF and here I have the right derived functor of of G, I should have. So in this setting, these total derived functors exist and form an adjoint pair. So if we have situation like this, then we will call these two functors, this adjoint pair, Quillen adjunction. Okay. And if moreover we have that for each cofibrant object A in C and fibrant object X of D, a map F from A to, so now we are in the category C, so we need to have G of X is a weak equivalence
it's already on.
Interesting. Then if we have a Quillen adjunction and the other condition is satisfied, then the statement of the theorem is that LF and RG are inverse equivalents of categories. And then this is definition of Quillen equivalence.
Definition one, this to be or this to be LF and RG to be categories.
No, I mean, so equivalence of categories is something more or less clear. What is that, right? So
yeah, no, but the definition to be equivalence is what after then or what before then?
before.
Before then.
Yes. So okay, Quillen equivalence. Quillen equivalence is a Quillen adjunction such that this condition is satisfied. Okay. So now I can discuss the other model structure on the simplicial sets with this Joyal model structure. So yes, in 25 minutes, no? 20 minutes. At least I will be able to squeeze up the definition. But the thing with Joyal model structure is that how we define the Quillen model structure on simplicial sets. We are saying that weak equivalences are weak homotopy equivalences after geometric realization. So what we are saying is that we are sending the simplicial sets to topological spaces, and then we are studying weak homotopy equivalences. There is a possibility of expressing this only in terms of simplicial sets, but this is not as it is usually done. Similar thing is with the Joyal model structure, because what is a weak equivalence in Joyal model structure? We need to have a homotopy coherent nerve, so, which sends a quasi-category to a simplicial category, and then it is a weak equivalence if after applying this functor, after applying homotopy coherent nerve, we'll get weak equivalence of simplicially enriched categories. So, but we haven't discussed simplicial categories yet, so I will provide the definition with which omits this condition. And yeah, I think I will be able to squeeze it, I hope. But maybe let me ask also, are there any questions? So just to say, also people on Zoom are allowed to ask questions if they want. Of course, I will provide a Joyal model structure, and I will not prove it. I will not prove that it gives model structure. So we will take it for granted. Okay, one more thing to say, kind of introductory. So the Quillen model structure on simplicial sets is well built in the way that it is relevant for studying homotopy theory of topological spaces. But so Joyal model structure will be the one which will be able to see the homotopy theory of quasi-categories. Yes, dot. Okay, so firstly, I need to give the following construction. So let C V be a model, be a category enriched over some monoidal category V and a monoidal functor from F to from V to U, from V to U, Yes, of course, if a monoidal functor, we are going to some other monoidal category U. One more thing to say. So up to this moment, I was basing on the Dwyer-Spalinsky's paper, Introduction to Model Category. I think this is the name. Right now, what I will be using is our notes to Dan Isaacson's talk on Joyal model structure, which was given at UWO at also reading seminar on quasi-categories. Yes. Okay. So then if we are in this setting, we can define an induced enriched category C over U by taking the same objects and okay, I need to have coherent notation. So homomorphisms in C over U between two objects X and Y. Well, this will be just image under my functor f of morphisms in C over V from X to Y. Okay. So having this definition, now let's come back to simplicial sets. So consider a functor tau1 from simplicial sets to category. So I think that by cat here I mean category of small categories. And it is defined as the extension So here we have simplex category included in simplicial sets. So we want to have this extension, or equivalently, the left adjoint of the nerve functor. And from cat to simplicial sets. Yes, right now, when I'm looking at this, I'm not sure if I am able to justify this diagram properly, so I would like to think about tau1 as a left adjoint to the nerve. I think what is happening here is that this is simplex category. It can be embedded as in simplicial sets as ordinary simplex. And here, I think this will be sending simplicial sets to, well, just its image in category of categories. Yeah, and then the tau1 is left can extension. Okay, so using this construction, we get this again, sorry. Of tau1. Yes, I will describe it in a moment. Well, the idea is rather simple. So you look at the graph. So you take only 0 simplices and 1 simplices. So this will give you a graph. A free category, yeah. No, I don't. I'm not sure. So how tau1 is defined in well, explicit terms. So you take as objects. So we start from a simplicial set X. As objects, you take vertices of X. As maps, you take edges of X. and then you need to make a category out of it. So if you have a two simplex, then you take a quotient of this free category by the two simplices, so it will give you just compositions. Yeah, so it is, yeah, more or less easy idea. I will write it down in a moment. Yes, I just wanted to finish this. So using tau1, what we get is a category of simplicial sets enriched over category of small categories. Say again, sorry? No, so what I will be doing is that this time I will be able to compose always. So I'm taking, okay, let me write it, because I actually wanted to write it. So a proposition is that given a simplicial set X, let F be a free category on the graph X0, X1. So by the free category, I mean we are taking, is just what I said. As objects, we are taking the vertices. As maps, we are taking the edges. And then we'll, of course, need to fill it with compositions. But then we define tau1 of X as the quotient of F by the relation induced by. So if we have two maps, sorry, two edges, F and G, right? So in my free category F, I defined the composition. So I kind of artificially added the composition. And I have, so this is supposed to be a two simplex. So I have another map, say H. And this H will be in a relation with G composed with F. Yes. So this gives us explicit definition of tau1. Okay, I have 5 minutes, so I'm going to speed up a bit. Yes, so a definition. So if we compose further tau1 with the functor from small categories to sets, sending a category to its set of isomorphism classes, then we call the. So you forget about maps, and there is a name for this skeleton of a category probably. So you are sending every object to no, sorry. So then first you are forgetting all maps, and points of your set will be isomorphism classes of the category.
Oh, of objects. Okay.
Yes. So we call the composition. We start from as simplicial sets. We go by tau 1. We land in categories. Then we use this functor. Then this will be, we'll call this tau 0. Is it the same as pi 0? No. Yeah. Okay. So let's. Yes. I mean small categories. So it will not be the same as pi 1 because pi 0, because what we, so consider this category. So here we have f, here we will have f inverse, and here we have some two morphisms, right? So what this will go to is set consisting of 2 points. So this one will go to this one, and these are isomorphic objects, so this will go to this one. But yes, and then it is not the same as pi 0 because this one is connected.
Yeah, so for example, the image of delta 1 is just 2 points.
Yes, and image of delta n will be just n points, n plus 1 points. Okay, I'm nearly there. So if we take this construction, so what we get, simplicial sets enriched over sets, so this is just ordinary category. Okay. So now, definition. So this will be the definition of a weak equivalence in the Joyal model structure. So a simplicial map is a categorical equivalence if it is an equivalence in simplicial sets enriched over categories. Now, I should probably say what I mean by equivalence in this setting. Yes. Second, sorry. Yes. Mm-hmm. Yes. So this is more or less the same idea as as in doing geometric realization. But
I think in unit of the category itself, every enrichment, you have here like because you have a map from the enrichment, you take two objects.
Yeah.
You have a functor between two the objects, right?
Yes.
Because you apply this, then you mean maybe that this functor
is an equivalence. Yes.
I think so. Because it's something like less than to say that it's like if you have two simplicial categories and the functor simplicial map between them.
Yes. Okay. I see. Yeah, you are right. Okay, so what is equivalence is, okay, let me say it again. So we have a simplicial map, right? And by this enrichment, it will give us a functor between two categories, right? So then we say that it is a categorical equivalence if it is equivalence of the categories in this enrichment. Yeah, okay. So now this is categorical equivalence. And we have a definition of simplicial map U from A to B is a weak categorical equivalence if tau 0 of U from tau 0 to B C to tau 0 of A C is a bijection for all quasi-categories C. Okay, so equivalently, I will not write this, but equivalently U is a weak categorical equivalence if instead of taking tau 0, we'll take tau 1 here. So this will be equivalence of categories. So the Joyal model structure is characterized by the following properties. So cofibrations are taken to be monomorphisms. Weak equivalences are going to be weak categorical equivalences. So if I had defined cofibrations as weak equivalences, I defined also fibrations, and fibrant objects are quasi-categories. Okay, so this is the Joyal model structure. Now, as a comment, here I will just say what are fibrations in this model structure. Okay, so firstly, what I wanted to say quickly is that because we have less, hang on. No, we have less weak equivalences because there are more fibrant objects. So every Kan complex is a quasi-category, but the inverse is not true. So we have less weak equivalences, so we have more fibrant objects. And what are fibrations? So fibrations are so-called inner fibrations. So these are maps which have lifting property with respect to only to inner horns, but we need the second conditions. The second condition, which is that fibrations are inner fibrations and isofibrations. So which means that if we have equivalence in the image, we can lift it always to an equivalence on the top. Okay, and I think I will stop here. So I took only 4 minutes more. So thank you. So any questions here or on Zoom? Yeah, we'll surely be back to the Joyal model structure.